Okay, so I sent you some half an hour ago some basic information about the exam. Let me quickly repeat it, and then I want to go through one old exam from the last year, which was written by Sven Raum. I think it's quite good and representative. Okay, so the exam will, so you have two attempts, one on January 13, which would be the written part. It will be, yeah, I'll put the exam on the course web page at 5 minutes to 9, and you'll have to 2 o'clock to write down things and another half an hour to upload it. So, but then there are a couple of students which have extended examination time. They would have another hour, but for the general audience, you have till 2 o'clock to solve it and upload. And the upload module would be on the same web page. And then on Thursday, I'll check it. And on Friday, we'll meet, maybe half an hour per student, to discuss some theoretical question for me to have some, idea whether you know some basics of the course or whether it's reasonable that you did your examinations yourself. And this would be on January 15, Friday. And then the second attempt would be at the end of February, will be the same procedure. Okay, so examination would be 5 to 6, maybe the first time 6, and the second maybe attempt 5 questions covering basics of the course, which is generating function, recurrence relations, Rook polynomials, Hamiltonian and Eulerian cycles, and a little bit about transport networks, cuts. And we haven't worked on finding maximal flows, but usually if you can find a minimal cut, it's not easy to guess how the maximal flow, you know the value and you look, graphs are not very complicated. In our examination, it would be usually possible, to guess what this thing is. In practice, of course, you have a huge network and then there is no chance you can do it by hands. But in our small examples, you can usually even guess. Once you know what the minimal cut, the value of the minimal cut is, you can take a look and see. Okay, so grades, I will announce on the text of the written exam. You'll get, the scores you need to have for the grades. And the oral exam is just the complementary. Oral exam is either fail or pass. So mainly what you did on the written exam would be, if you did things yourselves and you know more or less what is in the course, the final grade would be based on your score on the written exam. Okay, I guess this is it. I will be available through my, if you can mail me, let me put my mail and chat again. So if you have further questions, you can mail me later. Okay, now I don't think I have anything special to do to say more about this. So let me share the screen with problems and solutions of this of the exam, which took place exactly 1 year before, and we'll go through those. So do you see my screen now?
Yes.
Okay, very good. So we'll slowly go through this exam, and maybe I'll add a couple of questions of another exam which Sven Raum did a year ago, and then we'll go, slowly through the questions and solutions. And I think this would be more or less what I can do for you. There are more all the exams with solutions on your webpage, which you probably know by now. You can take a look during the holidays, maybe check other versions, because this course has been taught by different teachers and people have different styles. Although the book was the same and the major topics were the same, but the style of exams can be different, of course. Okay, so the first problem is about recursions and generating series. So the first theoretical question, yeah, I forgot to mention that oral exam would be mainly definitions, maybe some very easy, calculations of binomial coefficients or similar things, but really no heavy calculations, because I just want to check whether you know some basic notions of the course. Okay, so the first one is define the term generating series. Okay, what is a generating series? A generating series, if we have a sequence an, and from 0 to infinity, then its generating series is a formal power series, doesn't have to converge. It's just the sum n from 0 to infinity, an x power n or t power n, depending on x usually. It's a formal power series. Okay, B, so assuming that the generating series for a sequence an of real numbers has positive convergence radius and denoted it by f of x. Now prove that if we divide f of x by 1 minus x, we'll get the generating function for the following thing. The nth number would be the sum of numbers an from whatever, I guess 1 to infinity, 1 to n. We had this is just more or less the material of one section in the book. So it's again, you have seen this in the book. Okay, how should you do that? Well, we should look at this function f of x divided by 1 minus x as a product of f of x and times 1 divided by 1 minus x. And if we have a product of two functions, then if each of them is a generating series for something, for two different sequences, then the product of two functions is the generating function of the following thing. Here it is. So if I have f of x and g of x, and f of x is the generating function for a sequence an, and g of x is a generating function for a sequence bn, then their product would be the generating function for the following thing. It's the nth number would be sum of the products ak times bn minus k. It's called a convolution. Okay. It's in the book. I think it's called the summation operator, a small section there. Okay. And now in our specific case, we have f of x times 1 divided by 1 minus x. 1 divided by 1 minus x is just the generating function of the sequence of all ones. This is a 1 divided by 1 minus x, is a geometric progression. It's just 1 plus x squared plus x third, and so on and so on. So we can think of this product as, so f of x is a generating function for our original sequence an. And this second thing is the generating function for a sequence of all ones. And if we now apply this formula, so our b's would be all ones. So in this formula, what we have, we're just adding up ak's from 0 to n. So this thing would be the generating function of partial sums of the sequence an, in other words. Okay, that is what problem B is about. Now, problem C requires some calculation. It asks to find the generating function for the sequence of n cubed, n from 0 to infinity. Again, we have done this and you had some such exercises. And here you have an additional hint that you can use the information about the generating function of n squares to derive the generating function for n cubed. And the generating function for n squared is given here. It's this thing, x times x plus 1 divided by 1 minus x power 3. Okay, so we need from the generating function for n squared, we need to make one more step and find the generating function for the sequence n cubed. And to do this, we notice that this function has a positive convergence radius. It's well defined, at least close to the origin. Now, if we differentiate it, that means that differentiating it as this function would be the generating function of the termwise differentiation of this series. So if we would differentiate this series termwise, we'll get sum n cubed x power n minus 1. So it's almost what we need. And that's what it says here. So sum n from 1 to infinity n cubed x power n minus 2 is given by the derivative of the left-hand side of the previous expression, x times x plus 1 divided by 1 minus x power cubed. And so if we use the usual formulas for the derivative of a rational function, we should take the derivative of the numerator times the denominator minus the other way around and divide it by the square of the denominator. And this, after some simplifications, gives us 1 plus 4x plus x squared divided by 1 minus x to the 4th. And this is almost what we need, almost. It's a summation from 1 to infinity n cubed times x power n minus 1. If we additionally multiply it by x, we'll get the summation of n cubed x power n, and the right-hand side would be this thing multiplied by an additional factor x, and this gives us this answer. So that's what we want. So maybe I went a little bit quick through all this. Let me maybe slow down a little bit. So we want to find the generating function for this sequence n cubed, n equals to 1, 2, 3, 4, and so on to infinity. And we are given the information about the generating function for n squared. So for n squared, we also had this in the lecture, but that's just given to you explicitly like this. And from this, you need to derive the generating function for n cubed. And what you do, you observe that if you differentiate this series with respect to x, you'll get a summation of n cubed x power n minus 1. It's almost what we need. On the other hand, since this left-hand side has a positive convergence radius, we can interchange the summation and differentiate this thing. Okay? When we do this, we get that sum from 1 to infinity n cubed x power n minus 1 equals this rational function. It's somewhat straightforward, but calculations, but it's easy to make mistakes. So please, when you do such things, double check. And then the last step is that from this series sum n from 1 to infinity n cubed x power n minus 1, to get what we want, we just should multiply this by x. And we can do this, and we can multiply our previous result by x, and this will give us the required generating function. Okay, the next question in the next problem in part, the next part, the last part, D in the first problem here is using generating functions, solve this recurrence relation, satisfying the initial condition A of A0 equals to 1. And the recurrence relation is that the next entry, an, equals 2 previous entries, 2a by n minus 1 plus n cubed. This is a first order non-homogeneous recurrence. We also had such things in the book. Okay, and the idea to solve it using generating functions is that we are multiplying such equation by x power n and adding them up, so that after this addition of infinitely many such equations, the left-hand side after addition would be the generating function for the sequence an. And then, well, the right-hand side would be what will happen. We don't know at hand, but we'll see. It will be also possible to express this through the generating function of the sequence an. Okay, so let's see. So here is this question again. So we have this recurrence, which is valid for all n at least 1, and we have additionally a naught equals to 1. So multiplying this by x power n and adding them up, infinite number of such things, the left-hand side would be summation from 1 to infinity n x power n, which is by definition the generating function. Plus a naught. If we add up a naught, this would be the generating function for the whole sequence, which we denoted by ax. And what we have here with summation from 1 is f of x minus 1, because a naught is 1. So this whole thing is f of x minus 1. Now, what do I have here? Here we have, first of all, this generating function of n cubes. That's exactly the result of the previous part of this exercise. This thing is given by, we just calculated this. It's just given by this expression. And here we have, so this is almost the generating function which we want. The only thing, there is a shift. N minus 1 is multiplied by x power n, which means it's multiplied by x power n minus 1 and additionally by x. And there is a factor 2. So this whole thing is now 2x. Here is an extra parenthesis, which is a typo. It's 2x times f. So as the result, we can express f from this algebraic equation. We can move this to the other side. We can move this to this side. We have f of x times 1 minus 2x equals this thing plus 1. And after some manipulations, I haven't checked those, it seems that you are getting such a result. So this would be, if you want, now this would be the generating function for the sequence of numbers, for the concrete sequence of numbers we want. And if we want any specific entry, we should expand it in the Taylor series, which is possible here. It would be this polynomial. So each entry here is a geometric progression. So we can transform it into, 1 divided by 1 minus x would be 1 plus x squared plus x cubed plus blah, blah, blah. This is also a geometric progression, 1 plus 2x squared plus 2x cubed, blah, blah, blah. So in principle, at least in a computer, it's an easy exercise to transform this nice closed form for the generating function into a concrete recipe how to calculate each specific an. But this this form is actually preferable in many ways. It's compact, it's easier to work with probably compared to a fairly clumsy expression you can get for each specific entry an. Okay, now, so we are more or less done with the first exercise here. Now we're going to the second exercise, which is about graphs. So the first one, again, is a terminology question, a definition question. Define the term directed and undirected graph. Okay, so we start with a directed graph, which might be a little bit easier. So a directed graph is a set, a finite set. It's a pair. A graph is always a pair consisting of the set of vertices and the set of edges. Edges could be directed, undirected, weighted, non-weighted. Edges could have some additional structure. But the set of vertices is usually a finite set in most of the cases. So a directed graph is a set V and some subset of its Cartesian product, V times V. So a directed edge is a pair of vertices with an order, the first vertex and the second vertex. So it can be, it's just a subset of the Cartesian product of V times V. An undirected graph is almost the same thing. It's the set of vertices and some subset of unordered pairs of vertices. So in the second case, you don't care which vertex is the first one, which vertex is the second one. Yeah, okay, but you probably know that. Now the next exercise is find a planar representation of the graph K4, the graph K5 minus an edge, the graph K32, and the graph K33 minus an edge. Okay, so this is somehow related to what we discussed. We had this Kuratowski theorem, which was a criterion when a graph can be realized as a planar graph. So, and the result was as soon as your graph contains kind of a copy of K5 or a copy of K33, then it's not planar anymore. And the graphs which are listed here, they are still planar. Okay, I see. Let me check if I think he doesn't put his solution to this part here, but I can probably switch to my iPad and draw those things for you. Okay, let me do this quickly. Yeah, okay. Let's see if my pen works. Yeah, good. So I have to draw K4, K5 minus an edge, K32, and K33 minus an edge. Okay, so K with an index Kn is a complete graph on n vertices. You should know that by now. So K4 is, in other words, a complete graph on 4 vertices. It has it has 6 edges, and that's how it looks like in its planar version. So we need to find planar version of those graphs. Now K5, it's a complete graph on 5 vertices. So we can draw it like this. Now we have to connect, so each vertex should be connected to 4 others. So we have connected one of them to 4 others. Now we have to connect, let's see. So what is it that we're missing here? So we have to connect this with that, this with that. Okay. Yeah, so which one? So we have to skip one edge only. So this is complete. This is complete. This and yeah, and we cannot. This is also complete. So these three vertices are connected to all others, and this guy, which we have to skip this, otherwise we cannot realize it as a complete graph, as a planar graph, sorry. So this edge we have to remove. Okay, K32. K32 is a complete bipartite graph on 3 and 2 vertices. Yes, so K, yeah, I recall that K and M is a complete bipartite graph. So on N and M vertices, it has two groups of vertices, one consisting of N, another consisting of M, and each vertex in the first group is connected to each vertex in the second group and nothing else. So K32, I'm sorry, can be realized as a planar graph. Let's draw all we can in an easy way. So we can draw this thing. And now we have to connect these two guys in the first group with the remaining vertex in the second group, and we can do it like this and like that. Okay. Now the last thing is K33 itself cannot be realized as a planar graph. That's what this theorem is about. But if we skip one edge, we can do this. So let's try to do this. So we do that. Now we try to connect. So we can do this. We can do this. And we can do this. We can do this. And we can finally do this. But this remaining edge we have to skip because otherwise this is impossible. So this edge we have to cross out. So this is K33 minus an edge as a planar graph. Okay. Okay. So let me stop sharing my iPad and go back to the examination. So the next question is find an Euler cycle in each circuit in each of the following graphs. Okay, so here I think the circuit, the degree is even, okay. I think by a circuit he means a cycle. So it's a closed cycle going through all edges, yes, and coming back. Using each edge once and coming back. So I mentioned that the result by Euler says that a graph has an Euler cycle if and only if it's connected, of course, and the degree of its vertices has to be, every vertex has to be even. If we look at the top graph, we check. So this degree 4, degree 2, degree 4, degree 2, degree 4, degree 2, degree 4. This has degree 3. Okay, not good. This has degree 3, degree 2, degree 2. So in this graph, I also have to recall that we were talking also about Eulerian circuits. Maybe that's why he's talking about circuits. The Eulerian circuit is a path does have to be closed, such that yeah, such that you use each edge once, but you do not have to finish at the same vertex that you started at. And we can, to make this graph into a Eulerian graph, which will have an Eulerian cycle, we have to connect those. The criterion to having an Eulerian circuit as opposed to the cycle is that there are exactly two. Again, the graph should be connected, and there are exactly two vertices of odd degree. And this is the situation we have here. We have this guy, degree 3, and this guy of degree 3. If we connect them by a vertex like this, by an edge, I'm sorry, like this, we'll get a graph where all vertices will have even degree, and then we can get an Eulerian cycle. And if we remove from this Eulerian cycle this additional edge we put in, then we get an Eulerian circle.
Just a question. Cycle cannot repeat vertices, right?
Sorry? Yeah.
A cycle cannot repeat vertices, and an Eulerian.
Well, in cycle,
an Eulerian needs to visit every edge, right?
Yeah.
Are you sure it's not Eulerian circuit?
I think, I'm a little bit. I think the circuit doesn't have to be, or maybe Eulerian path. I forgot the terminology. I'm sorry. Maybe circuit is maybe
according to the circuit can repeat vertices.
Maybe maybe cycle, Eulerian cycle, and Eulerian circuit are the same thing. I don't know, but they were definitely something.
The cycle and circuit is not the same, so I don't think so.
Okay, and the cycle should be closed. The cycle should definitely be closed, and the circuit doesn't have to be closed. Okay.
Yes, the circuit has to be closed.
Huh? If the circuit has to be closed, then
an Euler circuit is where you can repeat the vertices, but you can only allow to visit an edge once, and you have to visit all the edges.
Sure. An Eulerian thing should use all edges, each edge once. But then there are cycles where you have to come back to the initial vertex, and they are paths, maybe. I think they're called paths. You have to use all the edges once, but you don't have to come to the same vertex which you started at. And there is a simple criterion for both. If you want the cycle, you have to have all degrees even. If you want a path, then you have to have exactly two vertices of an odd degree, and all the rest should be even. And in this graph, it's this situation where you have exactly two vertices of odd degree, this one and that one. If you connect them by an edge, then you get all degrees even. And so let's see. Anyway, if we want a path, we have to start with a vertex of an odd degree. Say we start here, and to get the path, I say I'm going 1, 2, 3 back here. Let me
just to clarify, a path you can't repeat vertices, but a trail can repeat vertices.
Okay, how would you call? Well, if we talk
an Euler trail, you can go from you go from one vertex to the other and visit all the edges.
Okay, trail maybe. Yeah. Okay. Because for Hamiltonian we cannot repeat vertices, but here for Eulerian we can repeat vertices, but we cannot repeat edges. Okay, maybe we call it a trail then, because here we definitely have to repeat vertices. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so go here, for example, 7. 8, 9, 10, 11, 12, 13, 14, 15, 16, and back to here. So we started here and ended up here, used all edges once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is one of the examples. There are usually many Eulerian trails. Okay, and here, I guess in the second one, let's see what happens here. So we have degrees 2, 4, 2, 4, 4, 2, 4, 3 here. Let's see, should be an even number of vertices of odd degree. So let's see, here we have 5. Yes, so there again two vertices, exactly 2 vertices of odd degree, here degree 3 and degree 5, which means that again it's possible to find non-closed trail which use all edges and starts at one of them and ends at the other. Okay. Okay, so now the part D, or let's see, I think we did, yes, we did ABC. Now we are at D. So here is the requirement, show this Euler theorem, so to say, but one direction. Show if there is a graph which admits a closed, I don't know, it's called Eulerian, I would call it a cycle, Eulerian cycle. Eulerian cycle, then you should show that the degree of each vertex has to be an even number. So that's one implication in the theorem of Euler's. And let's see. And the proof is trivial, so to say, because if we have an Eulerian cycle, we're using, and let us concentrate in the Eulerian cycle on the places where a given vertex appear. So this Eulerian cycle, if we count how many edges are adjacent to a given vertex, we'll look, say, at a given vertex V. It appears at several places in your cycle. But and we, first of all, we use all edges. In particular, in this cycle, they are all edges adjacent to a given vertex V. And then when we move along the cycle, there is an incoming edge and outgoing edge to a given V. So edges appears in pairs. Edges adjacent to V appears in pairs every time. So, and all edges adjacent to V are on the cycle somewhere. So that's why the degree of any given vertex has to be an even number. So we're looking at all places where V appears, and each time we see an incoming edge and outgoing edge, an incoming edge and outgoing edge. So they appear in pairs, and each edge in the graph appears somewhere. So all edges are accounted for, and they appear in pairs. That's why the degree of any given vertex is an even number. Okay, the last thing is E, to calculate the chromatic polynomial of an n cycle for n at least 3. Let me take a look at this, the solution. Okay. Okay, here is the solution. So the claim is that the chromatic polynomial of a cycle of length n, Cn, with this dummy variable x is given by x minus 1 power n plus minus 1 power n x minus 1 for all n at least 3. Okay, the chromatic number, I recall that so the chromatic So the chromatic number, if we fix a number of colors k, then the kth chromatic number of a given graph is the number of ways. So we're assuming that our graph has labeled vertices as well. So we're assigning a color to each vertex such that two adjacent vertices will not have the same color. And we discussed that chromatic polynomial satisfies a very interesting relation, which is called deletion contraction. So if we delete some edge from a graph, then its chromatic polynomial equals the chromatic polynomial of the original graph plus x times the chromatic polynomial of the graph obtained by the deletion, by the contraction of this edge. So we're identifying the vertices on the end of this edge. But we also had some exercises. Okay. So the degree of the chromatic polynomial equals the number of vertices. That's also what we know. So here, let's start with a triangle. Here is the base of our induction. For the triangle, we cannot cover, the triangle is also the graph K3. It's a complete graph. For a complete graph, the answer for the chromatic polynomial is really simple. So we cannot color it in one color. We cannot color it in two colors. And yeah, so there are 3 factorial ways to color it in 3 colors. So the chromatic polynomial of this thing is x times x minus 1 times x minus 2. And in general, if we have a complete graph on n vertices, so its chromatic polynomial would be a longer product like this: x times x minus 1, x minus 2, x minus 3, and so on, x minus n plus 1. Okay, so in this we can rewrite in the required form for n equals 3. It has the required form. Now, here, the next thing is that if we look at chromatic polynomials, they're fairly easy to calculate on a computer, but by hands, it's not completely trivial how to do this. But where graphs with very few, which are close to trees, are easy to handle. And that's our situation. So let's look at the path. For a path, we also had a formula, which is x times x minus 1 power n minus 1. How to get this? Well, if we have let's see. So if we have, say, k colors, so we can color the leftmost vertex in k different colors. K, we have this x stands for k. Now the next one we can color in all vertices but one, which we used for the first one. So it would be k times k minus 1. And it continues. The next one we can again color in k minus 1 in k minus 1 colors, and so on. As the result, we'll get this thing. Yeah. So now we have this formula, which is obtained by deletion contraction. So take a cycle and choose any edge and remove it. If we remove any edge, we get ln. For ln, we know the answer. And now the graph obtained by contraction of an edge in Cn is Cn minus 1. Yes, if we take a cycle and collapse one edge, we'll get a small cycle with one less vertices, of course. So this gives us the following simple recurrence, that the chromatic polynomial of Cn equals the chromatic polynomial of this path of length n, for which we have a formula, minus the chromatic polynomial of the previous graph. And apparently, if we work out the induction, it will give us this answer. This is a little bit tricky exercise, but it's still definitely not impossible to work out. Okay, so my suggestion is that we probably go through this exercise, through this exam, and this will be, well, maybe take another, maybe 30, 40 minutes, and this would be it. Okay, so exercise number 3 is about networks. So you will have to define the term flow and the value of a flow in a transport network. So I have to recall what a transport network is. It's a directed weighted graph, like here. So each edge has an integer weight called capacity, but there is an additional requirement that in a transport network, there should be only one vertex where all edges are directed outside. The incoming degree is 0. This is this guy. It's called the source, kind of the source of what, I don't know. And then there is one vertex of the opposite character. All edges are coming in, the outgoing.
Do we have a break, by the way?
Well, do you want a short break? Let's do this. Yes, not for too long. Okay, good. We'll do that. Yeah, let me share my screen again. Okay. So networks. So we're talking about problem 3 now. So I have to define the term flow and the value of a flow in a network. So network, I just recalled what this thing is. It's a directed graph with integer weights and one source and one sink. And what is a flow? A flow is a function on the edges, also integer valued function, non-negative, such that at each edge, the value of the flow does not exceed the capacity. These weights are called capacities of edges. And also it satisfies the important condition of equilibrium or balancing at each vertex except for the source and the sink. Namely, at each vertex, the incoming flow should be equal to the outgoing flow. Okay, and the value of the flow is what comes out from the source. And it's easy to prove that there is a formula to calculate the value of the flow using any cut. A cut is a separation of vertices into two disjoint subsets, one containing the source and another one containing the sink. And it's the difference from what goes from the part containing the source to the part containing the sink minus the other way around. Okay. Let's see, show that every cut and find them. So what we need to find the maximal flow and the minimal cut in this specific network. So here is a solution. I mean, here is this definition, what the flow is and what the value of the flow is. And they say that the maximal value of the flow is 5, and there is a cut which is so the value of the, let's see, the capacity of the cut is the following thing. the capacity of the cut, if we divide vertices into two groups again, one containing the source and another containing the sink, we count the total capacity of edges going this way from the first group to the second group, add them up. We do not count anything going back. And here is an example of a flow which has value 5. And you have to interpret this picture the follows. The first number here, so there are two numbers on edges with a comma. The first number is the capacity of the edge, and the second one is the value of the flow. So here is a big tube. Capacity is 5, but we just put 1 here in this direction. So we're putting 1 here, 2 here, 2 here. The total thing coming out of here is 5. And for example, here it goes 1 and it continues 1 this way, and we're not using any flow in this direction. Although the capacity is 2, the flow here is 0. And at each vertex, we see that the incoming flow, for example, comes in 1, goes out 1. Here there is comes out 0. Okay, and so we can check that the balancing condition is satisfied at each edge. Comes in 2, comes out 2. Nothing goes that way. So here 2 comes in, and 2 continues. Nothing goes that way, and so on. And for example, here at the sink, we have 1 coming in and 4 coming in, total 5. And here, total 5 comes out. And why is that the maximal? Because there is a cut. The Ford-Fulkerson theorem says that the maximal flow equals the minimal capacity of the cut. And where is the cut which has capacity 5? Okay, and the suggestion here is that we take these two vertices as the set which is denoted P complement, the one which contains the sink, and the remaining guys as the vertices containing the source. Then let's count what is the capacity of this cut. The capacity of this cut, so there are 2 edges going from the left side to this thing, this edge of capacity 1, and there is another edge of capacity 4. So the total is 5. So that's the minimal cut. Okay, so this is it for this question. Now problem 4 is about algorithms. We have to define the tree and the spanning tree. And then there is something about how we should label vertices, which one can think as vertices of the 4-dimensional cube. I can explain this. Okay, we'll start with the tree. So what is a tree? Let us talk about, say, undirected trees. An undirected tree is a connected graph with no cycles. That's the basic definition. And the directed tree is a graph whose underlying non-directed graph is a tree. What is a spanning tree? If we're given a connected graph, we want to find its subgraph on this exactly the same set of vertices, which is a tree. So we have to remove all cycles in a given graph, but keeping the rest connected, and then we'll get the remaining, the spanning tree. Okay. And here is the answer to the second part of this problem, which I think is a little bit tricky, maybe. So vertices of a 4 cube can be identified by sequences of zeros and ones of length 4. So we can either, so we have 4 positions for 4 directions, and we can either, if we draw a usual square in the plane, So we know that the vertices are 0, 0, 1, 0, 0, 1, and 1, 1. If we have a cube in the 3 space, so we have three directions that in each direction we can either choose a 0 or 1. In general, if we are in n directions, we can identify the vertices of the standard n cube with sequences of zeros and ones of length n. And here we're working with 4. So here is the list of all 16 possible sequences of zeros and ones of length 4. Now, how can we lexicographically order these things? So we had this. So this comes out of the section on rooted trees. So when we're discussing rooted trees, so we were saying that if we order somehow children of each vertex in a rooted tree, then we get a total ordering called the lexicographical ordering on the set of all vertices. And here's a special case of this situation. So, yeah. So two vertices in a cube are adjacent if and only if their labels, the sequences of 0 and 1s, differ at only one position. For example, this is the neighbor of that, this is the neighbor of that, this is the neighbor of that. So these two guys are neighbors, these two guys are neighbors, but these two guys are neighbors, but not this and this, because they, as soon as there are two or more positions in this record which are different, these vertices are no longer neighbors in the graph. Yeah. And so the lexicographical order here is the following. If we look at two sequences like this, and we look at the first position, which is distinct. So the guy which has a bigger, so the guy which has 1 in this position, he will win. He would be the bigger element in this lexicographical order. So you have to compare the records. You have to look at the first different position. One of the vertices will have 0 in this position, and the other one will have 1. And the one which has 1 independent, its further entries should be all zeros, and here the further entries can be all ones. But still, as soon as the first position is bigger, so this vertex kind of wins in the lexicographical order. Okay, now this I think is the last problem of the examination. It's about finite geometries. This was the last material we worked on quite recently. So the first sub-question is to define what a finite affine plane is. So a finite affine plane is this finite set of points and the finite set of lines, subsets of points with the following properties: that any two distinct points contain a single line, are contained in a single line. So through any 2 points, there is a unique line passing through them. Now, the second axiom is that if we have a line and a point which is not on that line, so there is another line passing through this point and which is parallel to this one, and parallel means it does not intersect it. And finally, the third condition is this non-degeneracy condition, saying that for any finite affine plane, there is at least a 4 tuple of points such that no line contains more than 2 of those. So that's the definition of an finite affine plane. And these 3 axioms lead to very nice properties. For example, we showed that for each finite affine plane, there is a number called rank, number at least 2, such that the finite affine plane would consist of n squared points and what was that? N squared plus n lines, and each line contains n points, and each point is contained as n plus 1 lines, and so on and so on. There is a nice classification result. Okay, now B in this thing is define and illustrate examples of planes of rank 2 and 3. And that's we did also in the lecture. Rank 2 is this thing, just 4 points, 0, 0, 1, 0, 0, 1, 1, 1, and 6 lines. And rank 3, we also discussed a series of examples coming from finite fields. So you can take a field, or you can fix a prime number, or maybe even its power, but say a prime number. And then you can look at the finite field of this order, which means that you're looking at Z mod, say if a prime number is Q, you're looking at Z mod QZ. And this quotient, the set of all conjugacy classes mod Q, would have an addition and multiplication turns out to be invertible for each class except for 0. So this thing, these guys will form a field. And yeah, in terms of number theory. Okay, and here is and now if we get an affine plane over this field, so we take the product of this field, the Cartesian with itself, and define lines in this as things satisfying linear equations in variables x and y with coefficients in this field. Then we get an example of an affine plane for any prime number and for any power of prime number. Here is a picture which we had on our lecture. If we take F3 and Cartesian product of F3 of F3, which contains of 9 points, then we should get, let's see, so these are 9 points, we should get n squared plus n, 12 lines. And here in this picture, we have 12 lines. So 6, so 3 horizontal, 3 vertical, 6, 3 additional, which are going skew that way and decreasing, and 3 additional, which goes that way and increasing. Okay, that's pictures you are supposed to know. This is also definition with a finite field. And the last thing was, what was the last part of this question is show that any finite affine plane admits at least 3 parallelity classes of lines. We went through this maybe briefly on my lecture. Let me go through this again, recall the definitions, and also recall how this can be solved. Okay, so lines so we call 2 lines parallel if they either coincide or they do not intersect. This was our major definition, and then we notice that if 2 lines are parallel, so the parallel being parallel is an equivalence relation, namely it's symmetric, each line is parallel to itself, and if a line A is parallel to B and B to C, then it's A is parallel to C. Okay, so the set of all lines splits into so-called parallelity classes, so whatever, finite sets of lines which are parallel to each other. Okay, good. And now we want to show, and we had also a little lemma on our lecture saying that in each finite affine plane, there are at least 3 parallelity classes, and this was used in our theorem. And the way to do this is through the third axiom, saying that there are at least 4 points, or 4 points, such that no line intersect any of these points more than twice. Okay. And now the idea is, let us pick, so we have points P1, P2, P3, P4, and we want to organize 3 lines which are not parallel to each other through these particular 4 points. And what we do actually, if I look at this picture, we take P1 connected to P2, there is such a line. P1 connected to P3, there is such a line. P1 connected to P4, there is such a line. And I'm saying that these 3 lines, P1 to P2, P1 to P3, P1 to P4, they cannot be parallel to each other. They lie into 3 separate parallelity classes. Why is that? Well, it's obvious again, because first of all, they have a common point. They are intersecting. So if they lie in one and the same parallelity class, they should coincide. But they cannot coincide because of this axiom. P1 and P2, the line passing through P1 and P2 cannot contain any of other 2 points, P3 and P4. That's the requirement of this axiom, that any line hits this 4 tuple at most twice. So this line cannot be that line, cannot be that line. So these 3 lines are pairwise intersecting at a common point P1, and neither of them can coincide with other. That means that they lie in 3 separate parallelity classes. Okay, I guess this is it. And I think you have additional info. Yeah, well, you have also time to prepare, and you have my email address. And please take a look at some other old exams with their solutions, which are all available. And I think I will finish now. And please, yeah, contact me maybe after the holidays. Yeah.
Question.
Yeah.
Yeah. So the oral exam, times for the oral exam, will you mail out, do the link, or how do we get a time? Or are we just given a time?
Yeah. So, well, first of all, I need to take a look at your exams. And then I'm not quite sure at the moment. Try to, if you probably know your preferences already, or maybe in some days you'll know how free you'll be on that Friday, the Friday which would be January 15. So I recommend you, if you already know that on that Friday I say can only these 2 hours, please send me your wishes, and I'll try to accommodate all of them. That's the only thing I can suggest. And it also depends. I mean, there are many students which were registered in the beginning, almost 60. I have no idea how many will actually take the written exam. And I'll be doing this with Johan also, because I mean, if it'll probably be at least 20 students taking the oral exam, I cannot do all of them myself. So we are more or less flexible, but the advice to you, if you have severe restrictions on this Friday, you can only do it this time or not that time, please send me your wishes, this information to me in advance. Yeah.
So you will have time, because the written exam is January the 13th, and then it says in this mail you sent that January the 15th, 2 days later, will be the oral part. So you're saying you will have time to actually correct all in 2 days. Okay.
Hey, well, I'll have to work hard. What can I say? So because actually lectures will for me, the lectures will start direct after that. I have to do this quite quickly. I hope I'll manage, because I'll have Wednesday evening and then I have all Thursday. This used to be enough. It again, I can hardly, if there will be maybe 20 to 30 written papers, this is not a big problem, since I'll be working with you on, if there will be, which I do not expect, 60, then I have to get some more help for that. But this is my problem. This is not your problem. Okay, well, Happy holidays and see you probably in January.